All right, so this video here starts the final section of this unit, which is looking at factoring. Whereas the last few videos, we're looking at effectively multiplying with polynomials. You know, every time you distribute or you FOIL something, you're multiplying. Well, factoring is the reverse of that. You're breaking something up into its factors, which kind of has to do with division. And really, you start factoring in elementary school. For example, I'll take a little pause from this. If you were asked in grade, I don't know, 5 or 6, to factor the number 12, I know you could break it up into 4 times 3. Or actually in grade 6, they'd probably write it like 4 times 3. So 4 and 3 are factors of 12. They're two numbers that multiply to 12. That said, 4 can be broken down even further into 2 times 2. And so again, doing some grade 6 math, if you're asked to fully factor the number 12, then eventually you want to break it up to 2 times 2 times 3. That is called fully factored. You've broken up 12 into all its factors. Each of these, the 2, this 2, and this 3, are all the factors of 12. So we'd say 12 has, in this case, 3 factors. So with that said, that's grade 6 math, roughly. Here we're factoring these, but we're factoring polynomials. And so how we do that first is by looking for the greatest common factor, the GCF, to say it a little faster. The greatest value that can be kind of pleasantly divided out of all the terms. When I say pleasantly, I mean no fractions, no decimals. And so for example here, the greatest common factor of these two terms starts with the number 5. Because 5, sorry, take that back, starts with 15. Because 15 is the largest number that can be divided out of both 15 and 45. 5, what I had before, was correct. 5 is a factor of 15 and 45, but it's not the greatest factor of those two. So 15. That said, there's more. This particular term here has a squared. This has just a. The greatest amount they have in common is a single a. So another part of my GCF is the a. A is the greatest common factor of a squared and a. And then I have the b term. This has b to the power of 1. This is b to the power of 3. The greatest they have in common is just a single b. And so 15ab, 15 times a times b, is the greatest common factor of both of these terms up here. So what I essentially want to do now is I want to factor it out. We say we want to pull out the factor from what we have up there, which really means I want to divide each of these by 15ab. That's what I'm really doing. Again, it's the reverse of what we did in the last few days, where you're multiplying or distributing out terms or factors. And so if I look right here, you know, the 15s will cancel out, 1a will cancel out, the b's cancel out. All that's left is a single a. So I'm going to erase. I want to make that a bit cleaner, though. I don't want to make it so messy. And hopefully, sooner than later, you can see how to get, in this case, just a single a by pulling out this factor of 15ab rather quickly. You know, ideally, we don't even have to write down that little step I'm showing there. That said, I also want to do the same thing to the next term. So I have negative 45 divided by 15 is 3. The a's cancel out. B cubed divided by b is b squared. And so what I've done now is I've factored the polynomial you had in the beginning. And it started with finding the GCF. And the GCF, actually I'll just label it right here, of these two terms was 15ab. That's the GCF of 15a squared b minus 45ab cubed. Before I go on to the next one, notice if I look at this backwards, if I gave you this and asked you to multiply it, the first thing you would do is distribute each of these, and you would get these two terms here and here. So again, the last few days we're multiplying, now we're factoring. It's essentially the reverse. We're unmultiplying. Although unmultiplying is not a word, but factoring is. All right, so same idea here. Let's look for the greatest common factor. The greatest common factor of all three of these terms, I'll do it like before by paying attention to first the coefficient and then each variable. If I look at the 15, the 45, and the 9, the greatest common factor of all of those is 3. 3 is the greatest common factor of all of those. Any number larger than 3 cannot be necessarily factored out of all of them. For example, 5 cannot be factored out of 9 without getting decimals or fractions. And again, when you're factoring out, that means essentially dividing. 3 is the largest number I could divide all of these by without creating decimals or fractions. Okay, that's my coefficient. For the a, I got a squared, a, and no a at all in the last term, which means a is not part of my GCF because I can't divide all of these by a. My last term doesn't even have an a. So Lastly, let's look at b. I have a b, b cubed, and another b. What's the most they all have in common? 1b. So 3b is the GCF of this trinomial up here. Okay, so I factor that out, so now I want to see what's left, which means, again, I effectively want to divide each of these by 3b. And I know, since 3b is the greatest common factor, I know I should be able to divide them all quite pleasantly. There should be no fractions, nothing weird should happen. That's what, otherwise we made a mistake with our greatest common factor. So 15a squared b divided by 3b. 15 divided by 3 is 5. A squared divided by nothing else is a squared. B divided by b cancels out. Next, negative 45 divided by 3 is negative 15. A divided by nothing else is a. B cubed divided by b is b squared. Last term, negative 9 divided by 3 is negative 3. B divided by b cancels out, and we're done. Okay, so again, when I factor this polynomial here, we end up with this. And again, if you look at this backwards, if I were to distribute this out, we would end up with this term. Right? So going this way is multiplying, going this way is factoring. All right. Let's look at not a lot of examples, but each a little bit different. So looking at these two, in fact, I'll focus on this one here first. I want to factor this, and the first thing, in fact, everything we're talking about today is always starting with, and is always going to basically be about finding the greatest common factor first. And other days we'll learn about some other things as well. So what is the GCF here? What is the greatest common factor of all of these terms? The greatest common factor is just a. There's nothing more than a I can divide out of all of them. Notice the last term doesn't have a coefficient, or has a coefficient of 1. And so, yeah, I can divide everything by 1, but that I don't need to write that down. And so the greatest amount that I can divide everything by is a. So I'm going to take out a factor of a. That's my greatest common factor. And now, to figure out what's left, I got to pull out that factor of a, which means I'm dividing each of these by a. And what do I have? I have 8a squared minus 12a plus 1. Right there, a divided by a is 1, not 0. A common mistake is to think there's a 0 there. In fact, it's such a common mistake, I'm going to write it down here. This is not correct. It's a really common mistake where people actually, honestly, the most common mistake is they don't even put the 0. They just leave it like that. But again, notice if that was correct, if you distribute this out, you would end up with 2 terms, not 3. So it cannot be correct. And again, anytime I write down a common mistake, I highly recommend you write it down as well. Again, that's a really common mistake when it cancels out. But again, yes, the a's cancel out, but anything divided by itself is 1, not 0. Let's look right here. What's the greatest common factor of all of these terms? Greatest common factor from all of them is a squared and a b. Nothing more can be divided out of all of them. Nothing greater than that. And so let's divide each of these by a squared b. And so if I pull out that factor of a squared b, what's left? Well, in the first term, I have a cubed divided by a squared is just a, and the b's cancel out. Minus 5, and all that's left is 5. Minus 5b, because a squareds cancel out. Plus 10, my a squareds cancel out, and I have just a b squared left. And again, like I keep saying, if you're ever unsure if you've done it correctly, go back and multiply, and you should end up with the exact terms we started with. And again, always starts by finding my greatest common factor. I will say, let's say you found a common factor but not the greatest common factor. Let's say you just had ab instead of a squared b. You could still factor it, and you wouldn't be wrong, you just wouldn't be done. You wouldn't have fully factored it. It's kind of like, going back to my example of 12, it's kind of saying 12 equals 4 times 3. That's not wrong, but if you want to factor it, you're meant to kind of break everything down as much as possible. In this case, it would be 2 times 2 times 3. And so if you don't take out the greatest common factor, it doesn't necessarily mean you've made a mistake. But if you're trying to fully factor it, which is what we're always kind of focusing on, you're just not done yet. You'll probably miss it as well. All right, last question before our final problem. These two. Okay, let me focus on this one first. So here, what's the greatest common factor? it's kind of weird looking because what I really have here, you can think of it as two messy terms. One term here and one term here. The first term is 4a times 2a minus 3. But it's kind of weird because that first term has this other binomial inside it. But fair enough. And the second term is 1 plus 2a minus 3. So what do they have in common? Well, 2a minus 3. They have this, what we call a binomial factor in common. Both of these two big messy terms have a factor of 2a minus 3 in common. And so that's our GCF. The GCF is not 2a, but 2a minus 3, the whole thing. A little bit weird, but basically a common factor can have multiple terms. And so what I want to do now is that's going to be I want to pull that factor out, 2a minus 3, and I want to see what's left. And again, when we pull out a factor, we're always dividing by it. And so if I look at the first fairly messy term, I have 4a times 2a minus 3 divided by 2a minus 3. Well, those 2a minus 3's cancel each other out, so all that's left is 4a. Plus, the next term, I have 1 times 2a minus 3 divided by 2a minus 3. The 2a minus 3's cancel out, so all I have left is the 1. And I'm done. And I took out a greatest common factor that was a binomial, which is kind of tricky, but especially if I highlight it, it's pretty clear that both these two messy terms have that in common. So a factor can actually have multiple terms. And that leads me to the last example before a final problem. So how do we factor this? Well, right now, if you look at it, there is no GCF. As it is right now, there's no GCF. There's no greatest common factor aside from 1. I mean, you can divide everything by 1, but that doesn't do us any good in this case. So essentially, right now, there's no GCF. However, I can create one if I do something called factoring by grouping, which means I look in these pairs. I'm going to look at the first pair and the second pair. Look in the first pair that I've underlined in red. That pair has a greatest common factor. The greatest common factor is 3a. And if I take out 3a from that first pair, I have a plus 2. Look in the second pair. The greatest common factor is 2, or negative 2. And if I take out a negative 2 from each, if I divide each of these by negative 2, I have a plus 2. So again, notice right here, if you focus on this, if you divide everything by negative 2, a negative divided by negative is a positive. A negative 4 divided by negative 2 is positive 2. Again, this is the hardest example of the day. At this point, though, I now have a question very similar to before. Now I've created the greatest common factor by grouping what I had originally into pairs. And so now there is a GCF. Now the GCF I can see is a plus 2 once I do that. And so like before, I want to pull that factor out and write it first. I don't have to write it first, but we always kind of do. And then what's left? Well, every time you pull out a factor, you're essentially dividing everything by your factor. So I'm dividing each of these by a plus 2 when I pull it out. And so that first term, 3a times a plus 2 divided by a plus 2 is just 3a. Minus 2 times a plus 2 divided by a plus 2 is just 2. And notice, if I actually went back and multiply this out, if I FOIL this out, a times 3a is 3a squared. A times negative 2 is negative 2a. 2 times 3a is positive 6a. 2 times negative 2 is negative 4. So I've kind of unfoiled in this case. This, most complex example definitely of the day. And again, honestly, if what we've done earlier was a bit challenging, then I wouldn't put much thought into this yet. But if everything else seems really straightforward, then yeah, you're ready to put some thought into this right now. But we call this factoring by grouping. Essentially, what we started with didn't have any common factors, but when I broke them up into pairs, I created and I found a binomial common factor. And that's going to come up again in a later lesson. So let's look at the final problem. As usual, for a lot of these final problems, I want to bring it back to some sort of visual, coming back to area. So like it says, the area of a rectangle is the product of its length and width. So in this case, the length and width are the factors, and the area being the product. And so if I look here, it doesn't really matter what we call length and width. But by convention, we usually say the longer side is length, the shorter side is width, but it doesn't matter. Okay, I'm going to call that length and width. So like I said, we can think of factors as being the length and the width. The area is the product. So in this case, we know a rectangle has an area of 8x squared plus 16. What are possible factors, or really what are possible examples for the length and width of that create an area of 8x squared plus 16? Well, there's countless examples. I'll list a few. For example, one possibility is if you literally just take out the greatest common factor of each of these. If you take out the greatest common factor, the GCF here is 8x. 8x is the largest value you can divide out of both of these. So if I take out that factor of 8x right away, I can think of that as being my width or my length times what's left. If I factor out 8x from all of this, I have x plus 2 left. And I can think of that as being my length or my width. And again, earlier on in this unit, I would give you something like this, and we would visualize this as a rectangle, and you would get to something like that. Again, everything we're doing is the reverse. However, 8x for the one factor and x plus 2 for another are not the only possibilities. Again, anything that would multiply to 8x squared plus 16x is possible. And so that's one possibility. However, another possibility would be the length. Let's say the length of the width is 4x. And if I took out a factor of 4x, I would have 2x plus 4 left. Essentially, I go back to 8x squared plus 16x and divide everything by 4x. And there's more possibilities. I mean, there's a whole bunch. I'll list out a few more, then I'll kind of stop. You know, I could also have 2x. And then if I took out a factor of 2x, I'd have 4x plus 8. So you can imagine the width being 2x, the length being 4x plus 8. Another example, I'll do two more, is just x. If I did that, I would have, not 4x, I'd have 8x plus 16. And one more example I'll give. Because it's not wrong to take out a factor of 1. It's usually not of any use. But in this case, it's totally fine. Take out a factor of 1. If you take out a factor of 1, I divide everything you see up here by 1, which means nothing changes. But I can still imagine a rectangle that has a width of 1 unit and a length of 8x squared plus 16. And I will say, taking out a factor of 1 eventually starts to become quite useful, especially for a lesson, a couple lessons from now. All right? But it's not wrong to take out a factor of 1. Just generally, it's usually not of any use, because anything, you can take 1 out of anything nicely. And that's where I'm going to stop.